Welcome to the third video on NC part programming. In this video, we are discussing about tool and tool offset refer to a CNC lathe. In a CNC lathe, the common methods of fixing the tool is on a hexagonal turret. So on hexagonal turret, we have got holes like this. These are actually holding the tools. So in the case of a hexagonal turret, the minimum number of tools that can be fixed on a lathe is 6. And here you can see in this picture, this portion is referred to as the reference point of the tool. That means at the face in which the center of the hole locates. But the problem is that when we are bringing the tool towards the 0 point of the workpiece, so workpiece 0 is set like this. Here it will be the workpiece 0. So when we are calling this tool to the workpiece 0, this tool reference point will come to this point. But in actual practice, we need the tip of the tool should come to this point. So that means we needed to offset this tool reference point to the tip of the tool. So in order to determine the coordinates of this offset, that is offset of tool reference point to the tip of the tool, we need the corresponding x-axis and z-axis. So that has to be measured, and these distances are actually referred as tool offset, and this measuring is done by a mean in the machine itself, and then we are measuring this distance and ended it to a particular portion in the control system. There is some table column like thing is there for entering the offsets of each and every tool which is used in an operation. So that will be stored in that particular address in the control system. In a milling machine, this tool offset is divided into two. That is, one is tool length offset and another one is cutter radius compensation. First, we need to set the tool length offset. So the tool length offset means the tool reference is usually at the tip of the spindle. So from here we have to shift this tool offset reference to tip of the tool. Okay, at the center of the tool at the tip. So it has to be shifted. So lengthwise in the Z axis we need to shift that tool reference point. So we need to measure that one. So in order to measure that one, first we need to down the spindle such that it will just touch on the surface of the workpiece here. So that method is known as the part datum method, and this is the easiest method. That in that method we have to bring down this spindle to downwards such that the tip of the tool will just touch with the workpiece. Then the distance will be measured by the system and it can be entered. That distance of Z can be entered into a particular column or otherwise a particular address related to this particular tool in the control system. Then it can be shifted to this point. The next method is 1, 2, 3 block. Okay, 1, 2, 3 block is a block available, standard block available. So instead of work surface, we are actually bringing the tool tip towards the block. The block is fixed on the table and on the surface, just such that the tool tip will just touch on the surface. Then the corresponding value of Z is entered into the control system for affecting such offset, tool length offset. And the best method is that there you can use a tool probe. So tool probe can be seen over here. So this one is a enlarged or magnified view of a tool probe. So at the top of the tool probe, we can just touch the tool. So the touch will be sensed by this probe and the probe will switch off the spindle. Otherwise, the movement of the spindle. Then the value can be recorded on the control system and the tool offset will be affected and on further program that will be added with the tool address. Next is cutter radius compensation. First, we will discuss the necessity of cutter radius compensation. If this is the tool for a milling machine, it has got a radius of R, and this one is a work, and on this workpiece we have to drill a hole like this. Okay, then this center line of the work will be the tool will be the the assigned reference center, and this will be the center of the workpiece, otherwise the hole. When we call this tool to align with this hole location, so when we are calling it using a program, then the center of the tool will exactly matches with the center of the hole. But when we are machining using the side cutting edge of a tool, actually we need to align the side of the tool with the workpiece. It is not aligning the center. So in this case, we need to offset that center to the side of the tool. That means we needed to offset a distance equal to the radius of the tool, and that is known as cutter radius compensation. So in CNC milling machines, we have got uh, three codes are used for cutter radius compensation, and here G40 is used for tool nose radius compensation cancel. When we are cancelling this one, when we are performing a drilling, reaming, or boring operations like this, when the center of the circle is exactly coinciding with the center of the tool, then we don't need any cutter radius compensation. So in that case, we will use this code G40. That means tool nose radius compensation cancel. But when we have performing an operation such like this one, when we are using the side of the tool, then we have to affect this compensation. So we will use G41 when tool nose radius compensation left. That means this is the condition of G41. That means that cutting tool is on left side of the workpiece. Okay, that is the case. When the cutting tool is on left side of the workpiece, we will use the code G41. This is for external machining, and for internal machining, you can see that this is the condition. The workpiece surface is here, and on left side of this one, the tool is actually moving. So here also we can use the code G41. And where we are using the G42. G42 is used for tool nose radius compensation right. That means the tool is on the right side of the workpiece. For external machining, this will be the condition because this is the workpiece. And on right side of that one, the tool is located and tool is moving in this direction. So we are using G42. And for internal machining, the situation is like this because this is the workpiece, and on the surface in which machining is happening, and on the right side of that one the tool is moving. So here also we are using G42. Next is a subroutine, or otherwise known as a subprogram. So when the subprogram is required, in some programming we need a series of commands which might be repeated several times in that program. Okay, if it is repeating like this, if we are writing all this program, it may be extended to few pages, so many pages. So in order to reduce that one, what we are doing, these repeating commands we are actually writing separately. That is, we will have a main program. Okay, we will have a main program, and we are also writing a subprogram. Subprogram will be a smaller one, but repeating in nature. So whenever we need to perform this subprogram operations, we will call the subprogram into the main program. After performing that one, that will be returned to the main command. Again, at the same some another location, again if we need this to perform the subprogram, again we are calling the subprogram to that location. It is performing. That means in order to reduce the length of the program, we are using subprogram, and it can be defined as it's a separate program called up by another program, otherwise main program. And the two codes are associated with the subprogram M98 and M99. M98 will be included in the main program. This is the command for calling the subprogram to the main program. And next code is M99, that will be at the end of subprogram. So whenever the M99 is reached, that means the subprogram ends here. It has to be, the command has to be redirected back to the main program. Okay, that's whenever the subprogram is called, the command will be moving to the subprogram, then it will be executed. After reaching M99, it will be came back to the main program. The subprograms are actually written by the operator itself, but we are now discussing another type of programs known as canned cycles. This is also used for reducing the length of the programming, but the canned cycles are actually defined by the manufacturer. So it has got some predefined structure. On that, some variables we need to enter, that's all, and all other lines will be pre-written by the program, by the manufacturer. So it can be defined as these are canned or fixed cycles. These are programming aids that simplify programming. Canned cycles combine many programming operations and are designed to shorten the program length, minimize mathematical calculations, and use minimal tool motions. Examples: drilling, peg drilling, tapping, boring, backspotting, facing, etc. And difference between drilling and peg drilling is this one. If it is a block, drilling means we are performing it directly. If we are with a single pass, if we are drilling this one, this is the drilling operation. But on the other hand, if the depth is more, the peg drilling means we will first move the tool to a certain distance, then it will be taken back, then it will be moved to further distance, then again it will be taken back, and finally it will pierce this material and make a through hole. So it is the practice we are using for drilling deep holes. So that is the peg drilling cycle. So these are the some examples of these cycles or canned cycles used in numeric operating system and in FANUC system. In the next video, we will have a practice on writing a program. Thank you for watching.